I'll give you one more example. In this example, we are not given the function. We have to generate the function for that one. We're given the information. This is our mathematical model. We just change it to mathematical model by deriving the equations from the given description. Find the three positive real numbers whose sum is 1000 and whose product is maximum. That's the question. So we just suppose we say we're having here three real numbers. We say this, let x, y, and z be the real numbers. So from these real numbers, we want to find these real numbers. The information we are given that the sum is 1000. So we say x plus y plus z is equal to 1000. This is my equation 1. The second information given to me is the product of these three real numbers. The product is the function. Here is x, y, and z is equal to x, y, and z. This is my second equation. I just changed this f to the capital F because I need to bring the small f for this purpose. In this equation, we have the variables x, y, and z. We are studying the maxima minima for the function of two variables. We not have discussed anything for three variables. So we have to use this two information given in equation 1 to change the function to two variables. So we get the value of z from equation 1. Value of z is equal to 1000 minus x minus y. And then I substitute this information in number 2. So we're having x, y. I get here 1000 minus x minus y. Now I say this is my function of two variables, x, y. This is my equation 3. So this equation 3, with the help of that one, I find the value of x, y, and z, which give me the maximum value of the product under the condition we have already defined. So before going further, I would like to say that please subscribe the channel and press the bell icon so that you can get the latest videos which we are generating for you people. So number 1. Number 2, we have given the reference in the description for my notes, and you can get the notes from there. Number 3, as I always say, that you can learn mathematics by doing practice. So in my notes, they are given more examples and more exercises. With the help of these exercises, you can master this course. And also, if you go to any book of the calculus, the chapter of the partial derivatives, this extrema function of several variables come, and there you get many questions that you need to solve so that you can have the practice. So I go further. I have the function, and I just do further multiply by xy. So I get here 1000 xy minus x square y minus xy square. Now this function, I am going to solve it, and I will find the critical points, discriminant, and also then I decide about the maximum minimum. To find the critical number, so I just take number 1. I find the partial derivatives. The partial derivative with respect to x. I'm going to have here the partial derivative with respect to x. That I will get f of x. Y is constant. We get here 1000 y minus x is to get here 2xy minus y square. So then I find the derivative partial with respect to y. X is constant, so we get here 1000 x minus respect to y. I get here x square, x to y 2xy. This is my equation 4, and this is my equation 5. So whenever I say I want to find the critical numbers, we know that the critical points, we note that we substitute the derivative of the function f of x equal to 0 and f of y equal to 0, and we solve it to get the value of x and y. I substitute here, I get here this new equation, 1000 y minus 2xy minus y square equal to 0. This is my, I say, equation 6. And then I have 1000 x minus x square minus 2xy equal to 0. This is my equation 7. Now we can see here, I can take y common. I get here 1000 minus 2x and minus y equal to 0. So here this y equal to 0, or we having 1000 minus 2x minus y equal to 0. But you say y is not equal to 0. When y is equal to 0, then the product is equal to 0. We want to find the maximum product. This means that we are having here equation 1000 minus 2x minus y equal to 0. This is my equation 8. Now I can take here the second equation, number 7. Equation 7 we take, and from equation 7 we take x common. We get here 1000 minus x minus 2y equal to, again the same argument, x is not equal to 0. When x is equal to 0, then the product is equal to 0 because we want to find the maximum value of the product for the value of x, y, and z. So it means x is not equal to 0. That means that give me here 1000 minus, I'll get here x minus 2y is equal to 0 is number 9. Now I want to solve these two equations to get the value of x and y. To solve this equation, I just multiply one of the equation with 2 and add to the other one. I multiply this equation 8 by 2 minus 2 times equation 8 plus equation 9. When I multiply this one by equation by minus 2, 8 we get minus 2000 minus 4x become here plus and get here plus 2y equal to 0. Now equation 9 is 1000 minus x minus 2y equal to 0. When we add them, we get here minus 1000 plus 3x equal to 0. This give me here 3x is equal to 1000. X is equal to 1000 over 3. So that's only one value of x I got. So I want to find get the value of y. I can substitute in any one of the equation. I substitute in equation 8. We say from equation 8, I substitute in equation 8. So I will get here this 1000 minus 2x. This 1000 minus 2x minus 2000 over 3. And then here is minus y equal to 0. So I simplify this one. I get this is simplifying this. We get here 1000 minus over 3 is become 3000. We get here 1000 over 3 minus y equal to 0. And they give me the value of y. The value of the y is 1000 over 3. So I have only one critical point. My critical point is xy, that is here 1000 over 3 and 1000 over 3. So we need to check at this point that we get the value of the product as a maximum. So for that one, we use second derivative test. To get the second derivative test, what I need here the second derivative of the function. Here is the first derivative. So I'm going to define here the second derivative. I find here f of xx. What's my f of xx? Here x is changing, y is constant, this is 0, this is 0. I get here minus 2y. Then I find here f of xy. This means x is constant, y changing. We get here 1000. And we get here f of y is equal to minus 2x minus 2y. This way I differentiate respect to y partially. So my x is constant, it's only here 1000, y is 1, here y is 1 minus 2x, here y is 2y. Then I get here f of yy. My f of yy, x is constant, we get here minus 2x. So this I get here the value of xx, yy, and we can use this one to find the result. I find the value of f of xx at the point I'm having here 1000 by 3. So we have this point, I get here value of f of xx at the given point. I write here point AB. As we have one, they say A is 1000 by 3, B is 1000 by 3. So we get here minus 2000 by 3. And if I find f of xy, my xy is 1000 minus 2000 by 3 minus 2000 by 3. I simplify this one. I get 3000 minus 2000 minus 2000. That's become here minus 1000 by 3. And this is my f of xy. So just I rewrite here more clearly. That's my x, and here is my x and y, xy. So then I'm having a f of yy. We put here the value of x is 1000. It's minus 2000 by 3. So these are my values. And these values help me to find the discriminant of my function. So discriminant of my function is, here I can have here discriminant, this is the discriminant of the function, dxy is equal to f of xx, f of yy minus f of xy whole square. I've already calculated the value of a function at point 1000 by 3. This is my critical point, only one critical point, 1000 by 3. And the value of f of xx is minus, here I have just calculated it, and I'm having the value I have, this is minus 2000 by 3 minus 2000 by 3. So I get here minus 2000 by 3, multiply the value minus 2000 by 3 whole square minus fxy whole square. Fxy have value minus 2000 by 3. This here is minus 2000 by 3 whole square. So obviously we're having here this 2000 by 3 into 2000 by 3. We are having the plus value and minus 2000 by 3. So the value of xy is 1000 by 3. I'll make a correction here. This here is 1000 by 3. And now we can see here, this become here, minus might become plus, and get here 2000 power 2 by 9. And get minus here, and this is 1000 whole square over 9. Now this is obviously bigger than 0. So when discriminant is bigger than 0, when d is bigger than 0, this implies there is extrema. So it can be local extrema, it can be local maxima, or it can be local minima. So that's clear. If it is less than 0, it means saddle point there is no maxima, minima. Now we check here by using second derivative test, maxima, minima. We have a second derivative test, and we find here f of xx, at xy, and the value of this one here we have calculated. We can take f of xx or f of yy. So this value is minus 2y. Here is equal to minus 2y. And the value of y, we are having a minus 2 into value of y. The value of y we having calculated here. That is here 1000 by 3. So we are having here 1000 by 3. And this value is less than 0. We can take f of xx or f of xy. We should substitute the value. This is the value of f of x at the point. This here is the point we have taken. And then this is less than 0. This implies is local maxima. So this means we're having local maxima for this function at the point 1000 by 3, 1000 by 3. So we can find the value of x, y, z. Our x is 1000 by 3. We want to find 3 values. Or y is 1000 by 3. We want to calculate value of z. What's the value of z? Value of z is equal to 1000 minus x minus y is 1000 minus 1000 by 3 and minus 1000 by 3. When calculate it, we get again 1000 by 3. So required values for the maximum value of the product, that's the values such that product is maximum. We get here the values. Here x is equal to 1000 by 3. Value of y is equal to 1000 by 3 and value of z is equal to 1000 by 3. So this is the result of our function. That's the idea. We can have many, as I told, there are many other examples. Different type of example you'll find when we're having some function, there is some condition, and we can use our conversion that from 3 variables, we can bring into 2 variables, and then we can just solve it. It can also happen that we're having 2 variables, we bring it to 1 variable and we solve it as we have done in the earlier course of the calculus. So that's the idea for finding local extrema of the function.